This is the most terrifying sight that anyone traveling on the road would want to avoid. That's also why the US government spends between $30 and $50 billion annually on 45,000 miles of rigid pavements in the Interstate Highway System. In return, each mile of road built can withstand thousands of tons of load per day, yet its lifespan can still reach 50 to 60 years. Behind these familiar roads lie technologies that will amaze us. UHPC supermaterials can withstand the load of vehicles weighing 40 to 100 tons. Those massive machines, equipped with laser scanning sensors, manage flatness down to the centimeter. Automated construction systems minimize errors. This ensures the production of a uniform, straight layer of concrete over hundreds of miles. In this video, join us as we watch how American engineers create the world's most durable roads. In the US, asphalt roads account for a large proportion of the country's road network. However, rigid pavements are becoming increasingly popular, especially for use on important national roads, due to their durability even after 30 years of use. In addition, concrete is less prone to deformation than asphalt at high temperatures, preventing sudden collapses like this. Construction time is also not an issue thanks to the Slipform Paver machines, which allow concrete to be spread over a width of 18.75 meters, or 61.5 feet in a single run, and can operate continuously for 24 hours. The first step in constructing a concrete road is the planning and design phase. The Department of Transportation and geotechnical survey teams in the US widely use drones as a logistical tool for collecting topographic data. Since vehicle load and the number of vehicles passing through each day determine the stress that the structure must withstand, engineers need to accurately determine the traffic flow, vehicle types, vehicle weights, and their expected increases. Next, a geotechnical survey is conducted to understand the soil characteristics, such as moisture content, strength, and the required soil volume, to design the concrete structure so that it does not shift, crack, or deteriorate prematurely. Drones perform aerial surveying using photogrammetry and/or LiDAR to capture high-precision elevation points and surface imagery of the site. The collected data is processed into a three-dimensional point cloud, elevation maps, and a full topographic three-dimensional model that engineers use for road alignment design, earthwork volume estimation, and construction planning. Drone mapping can provide topographic maps and three-dimensional ground models, orthomosaic maps, contour lines, and accurate point clouds that engineers can chain to design software to plan construction projects. Data collection using drones enables faster, safer, and less costly surveys compared to traditional manual surveying, especially in large areas or complex terrain. The engineers then select the type of pavement, usually JPCP or CRCP. Next, they will simulate the road and drainage design, the most important aspects of a concrete road, on CAD and simulation software using methods from the AASHTO. The thickness of concrete pavement in the US depends on the expected load and design conditions, commonly 10 to 12 inches for highways with heavy loads. However, it can be up to 14 inches for very heavy loads or weak subgrades. Jointed plain concrete pavement, the most common type, has a slab thickness of at least 8 inches, up to 15 feet. After the design is approved, the next step is step 2, site leveling and excavation work. Vegetation, topsoil, and organic matter will be removed. Construction on steep hills is impractical and dangerous due to numerous blind spots. Therefore, leveling the ground is necessary. This process involves leveling higher areas of land and using that material to fill in lower areas. Safety principle. Reducing the slope of the road will increase the driver's visibility, giving them more time to react to hazards. To prevent the vehicle from flipping over at high speeds, the outer edge of the curve is raised. This design provides the necessary centrifugal force for a smooth turn. Temporary erosion control measures were installed in preparation for the 4 main structures during road construction. Subgrade. Natural soil is compacted to form the final foundation, bearing the entire load from the layers above. Subbase. A mixed or stabilized soil layer, sometimes containing aggregate. Its function is to provide additional support, distribute weight evenly, and aid drainage. Base course. The strong, load-bearing layer directly beneath the concrete, effectively distributing loads and providing structural rigidity. Concrete slab. The top, rigid layer in direct contact with traffic, provides a durable, non-slip driving surface. Natural soil is leveled to the final elevation and compacted to a specified density. A test roll helps identify weak points. Next comes the installation of the drainage system. Lay drainage pipes both vertically and horizontally. Underground drainage will be installed along the edge of the sidewalk if necessary. The culverts and horizontal drainage structures were constructed. Water management work was completed before the road surface layer was constructed. According to the AASHTO guidelines, good drainage and slope design is crucial to avoid cracking and pavement defects, including drainage slope. The surface must be sloped evenly to direct water away from the pavement. Subsurface drainage, using perforated pipes or a permeable layer beneath the slab to prevent water from pooling under the slab. Edge drains, drainage systems along the edges of roads to reduce moisture buildup underneath. Slope crown, the longitudinal crown is typically approximately 0.5 to 2%, ensuring adequate drainage. Apply a granular or cement-treated subbase. Typical thickness ranges from 4 to 8 inches, provides even support and prevents shifting. The subbase is compacted and properly graded. The automated cutting machine shapes the substrate with high precision. Accuracy is typically within plus or minus 6 millimeters. It uses a laser or GPS-based machine control system. The next crucial step in increasing the road's load-bearing capacity is load transfer and reinforcement placement. The pins are inserted into the horizontal joints using a basket or insert tool. The bracing bars are placed along the longitudinal joints. For CRCP, the reinforcement is arranged continuously. Alignment, depth, and spacing are strictly checked. The most important ingredient is concrete, which is mixed at centralized or mobile plants. They were then quickly transported to the construction site. A standard concrete mixer truck in the U.S. typically carries about 8 to 10 cubic yards of concrete per trip and delivers nearly 3 cubic yards per hour. Volumetric mixers can achieve approximately 24 to 34 cubic yards per hour when mixing directly on site. The mixture consists of sand, stone, cement, and water mixed in specific proportions. UHPC is particularly notable for its very high cement and fine aggregate content, along with extremely low water content, resulting in superior waterproofing and exceptional durability. Look at this giant machine resembling a mobile building. It can pave a width of 18.75 meters, allowing for the construction of a 4 to 6 lane highway in a single run. Concrete is poured in front of a sliding paving machine. The paving machine spreads, compacts, and shapes concrete slabs in a single pass. The internal vibrator removes air bubbles. The thickness of the concrete layer is automatically controlled by a 3-dimensional GPS or robotic total station system to print the line, accurate to the millimeter. Next comes the initial scraping and smoothing process. The surface is textured by dyeing or stretching the fabric. The structural orientation was selected based on noise reduction and drainage performance. Next is joint construction, which is extremely important in controlling crack formation. Cut the joints with a saw within 4 to 12 hours after pouring the sugar. The depth is usually 1/4 to 1/3 of the concrete slab thickness. The curing process is necessary to prevent concrete from losing moisture and cracking due to heat. The curing agent is sprayed immediately after completion. The curing process is maintained for at least 7 days, and traffic is strictly prohibited during this period. The engineers will then conduct quality control and testing. Concrete strength is tested by taking a cylindrical core. Check for smoothness using a surface roughness meter or IRI. The United States uses the International Roughness Index, IRI, to measure road quality, with a much higher threshold for good roads than many other countries. Over 80% of the length of federal highways is rated as good or very good. The joints are cleaned and sealed with silicone or hot melt sealant. This prevents the ingress of water and debris. Final tasks: road marking, installation of guardrails, signs, and lighting. The road was opened after meeting the requirements for durability and flatness. Typically, the drying time ranges from 14 to 28 days after asphalt application, depending on the mix and design.